Assalamualaikum warahmatullahi taala wabarakatuh. Okay, see you again. Today I discuss example for the boundary layer. This is example 3.1. Okay, in this example, the question given to us is a smooth flat plate of length L equal to 6 meter and width B equal to 4 meter is placed in the water with an upstream velocity of 0.5 meter per second, and then determine the boundary layer thickness and the wall shear stress at the center and the trailing edge of the plate. And then they said that assume the laminar flow boundary layer. So first step when we're going to solve this one, I start with draw the um, boundary layer profile that develop. Okay, this is the flat plate inside the water. So we have this flat plate inside the water, and then the flow come from this way. So this is a velocity came from this way. Since the plate go this way, so the velocity you note then the boundary layer develop here. So from this boundary layer developments, and then we have at the center of the plate. So the total length of the plate is 6 meter. So we have this plate 6 meter, and then this is at the center of the plate. So the first question asks us to determine the delta and the tau wall. This is a tau wall. No? This is a tau wall at the plate. So we have a shear stress, or I put as a tau wall. So we're going to determine this delta here. So we have a delta here, and also the delta and the boundary layer at the trailing edge. So we have this boundary layer here, the velocity profile here, and then we also have a velocity profile here, this trailing edge, and then we also have here, also we have a delta, new delta. So delta 1 and delta 2, tau wall 1 and tau wall 2. All right, so we have these two situations, or these two positions that we're going to measure. And then we know that the first thing we're going to measure is at the, so the summary of the question is we need to find the, we need to find the delta and tau wall at x equal to 3 and x equal to 6. So this is x come from it. So this is x, and then this is y. All right, so now we're going to solve this. So we know that this is a flow through the water. So the two properties of water that we must know here is one, density. So I take as density here as 1000 kilogram per meter cube, and then this is a dynamic viscosity, which is I take as a referred to at the temperature of 20 degrees C, which is the the mu is equal to 1.12 multiplied by 10 of power minus 3 Newton second per meter square. All right, so this is the data that we have. We have this data, and then we're going to get this. So we assume that is a laminar flow. So what we assume that we assume laminar flow. So from this laminar flow, I will take this as I assume this is a laminar flow, and then I, we can take this as okay, assume this as a laminar flow, and then the boundary layer assumptions that I choose here is we take the exact solution which is come from the Blasius. All right, so we take the Blasius under extension. So I use such a laminar flow, and then the boundary layer here is a boundary layer from the uh, boundary layer thickness is from the Blasius. So from the Blasius, so the delta is given by 5.055x 5 5x divided by square root of r e x. Okay, so this is a delta, and the tau wall. Okay, from the Blasius we know that the tau wall equal to rho at cf rho u naught squared over 2. Or, and then the cf, we know here the cf from the Blasius is given by 0.664 divided by square root of r e x. So now I substitute this into this equation. So the final, I got the TW, this is equal to 0.332 u naught 3 over 2 then by square root of r mu divided by x. Okay, so from here, now we have these two equations. We know already these two equations, and then now we can solve this problem. Okay, let we solve this problem. All right, now first I try to solve at the center of the plate, which is x equal to 3. So at the x equal to 3, we just substitute because we already know the delta. So delta equal to 5x divided by square root of rex, which is rho u naught x divided by mu. So if we substitute this value inside here, so we got the 5 multiplied by 3, and then we divide by square root of 1000 multiplied by u naught is a given here. If you look at here, the u naught is a given here as a 0.0.5. I forgot to put here u naught equal to 0.5 meter per second. All right, so now you put this 0.5, right? The x is a 3, and then divide by 1.12 multiplied by 10 power of minus 3. So if we solve this, we can get the answer for the delta here is a 0.013 meter. Right? This means that the delta from the here, this is the boundary layer. So this value of this delta is a 0.03 at x equal to 3 meter. All right, now the second one, if we solve the tau wall. So what is the tau wall? Tau wall is equal to, as as I said just now, this is 0.332 u naught 3 over 2 square root of rho mu over x. So if we substitute all those value given to us, therefore we have a 0.332. So multiply by 0.5 over 2, then multiply by square root of 1000, 1.12, and divide by 3. So if you calculate this, you will get the answer is 0.0716 Newton per meter square. Alright, this is at the center. At the trailing edge, which is the next is at the x equal to 6. The trailing edge means that they find the end of the and the length of this. So this is a similar procedure that we put into the this problem. So what we do, the delta against 5. I just substitute here. This is a 5 multiplied by 6 divided by square root of 1000. U is a 0.5, and then by 6, okay, divide by 1.12. So at the end of the day, we have a delta for here is a 0.0183 meter, and then the tau wall also similar. So we have the 0.332 multiplied by, I just substitute here, 0.5 power of 3 over 2 multiplied by the square root of 1000 multiplied by 0.1, sorry, 1.12 by 10 power of minus 3 divided by, which is x is 6. So in this case, the value for the tau at the trailing edge is equal to 0.0506 Newton per meter square. So now we have all this value. We got all those results in here. So we have the result for the delta at the center of the plate is a 0.013, and then the shear stress is a 0.016, and then at the trailing edge we have a delta equals 0.0183, and then the wall tau wall equal to 0.05. Okay, that's that. I think this is an easy example, and I hope that you can understand this. And then we use totally the Blasius solutions for this in order to solve this. Why? Because of the not mention what type of velocity profile. So I assumes that, and we assumes that we use the exact solution, which is using the Blasius. Okay, with that, thank you very much.